This is video 1.1. It's about the algebra of sets. In this video, we're going to look at ways to make new sets out of ones that you've got. So ways to combine or complement the sets that you already have. Right, let's go. So here are some definitions of things that we might do to sets. And I'm going to talk about subsets for this. I'm going to imagine that you have some large set S and that we're talking about some subsets A and B. And that's partly so that when I talk about complement in a moment, I've got something to work with, some limit to the universe of potential elements. So we're working in S for sandpit or sandbox, the place where we're working today. So given subsets A and B, the union, written like this, A union B, that's not quite the letter U, that's something a bit different from the letter U, but you should probably avoid using the letter U and this symbol at the same time anyway. So A union B, that's the set consisting of those elements that are in A or B, by which I mean A or B or both. I always mean that when I say or, but I've spelt it out this time, just to be clear that I'm using something that you might call inclusive or all the way through. So that means that A union B is the set of elements in S such that X is in A or X is in B. So remember this notation on the right with the curly brackets and the colon means that I have a set and I'm slicing out some of the elements. I have this property on the right and you have to satisfy that property to be in this set. So the union here is things, it's quite permissive, is things that are in either A or B or both. The intersection, which I will admit that in my head I sometimes pronounce intersection because I'm trying to remember this symbol which looks a bit like an N, is the intersection symbol. So A intersect B, that's the set consisting of those elements that are in both A and B, like this. So A intersect B is the elements of S that are in A and also in B. So that one's not so permissive. You've got to reach both of these conditions, X being in A and also X being in B, in order to be in the intersection. Two more. I have the complement of A. This is why I've set up a sandpit to play in, a wider universe of elements. This is the elements not in A. So it's sometimes written A complement with a C, where you might put an exponent for a power, like A squared or something. AC, C for complement, or sometimes people put a prime there. I think I've also seen bar along the top for the complement. Hopefully whenever you're reading a book or lecture notes or something, they will make it clear what their notation means. That's the subset consisting of those elements that are not in A. So that is elements of S that are not in A. And you see I have to set up a universe of elements here, otherwise, oh gosh, it escapes and it contains crazy things. We run into Russell's paradox and things like that if we're too generous with what we'll allow to be in A complement. So the set difference, or the complement of B in A, and that's written A and then a backslash B. That's the subset of A consisting of those elements that are not in B. So to get here, I've written this as X in A such that X is not in B. And I could write that out as the elements of S, which is how my other definitions start, the elements of S such that, and then there would be two conditions. You have to be in A and not in B. And that's this intersection, right? When you've got two conditions, X is in A and X is not in B. So that set difference has this other way. You can define that using the things that we just defined, intersection and complement. So this is, if you like, a little bit like subtracting out the elements. You have the elements of A, but not B, not those ones. Take those away. I want to talk about the other elements of A, which might be the empty set if you take everything out. It might be the same as A if you take nothing out, but elements of A, subset X is not in B. Notice that B is not required to be a subset for this notation at the end. So when you see this being used, you can't assume that B is a subset of A. It usually is, but the definition there doesn't require it. It doesn't do anything in terms of the definition. If B's got some more elements hanging around that are not in A, because of course you have to be in A to be in this set, but you can't assume from the notation that B is a subset of A. Okay. Here are some diagrams. Some people find these helpful, I think, for visualizing what's going on here. So the union on the left, A union B, which I sometimes pronounce A or B, but that confuses things a little bit between the logic which applies to the elements versus the set operation of unions. I'm going to try and say A union B. That's permissive. It's anything in A or B or both. That's allowed. The intersection here is less permissive. It's the things that are in A and also in B. So I've shaded in this middle bit. The complement of A is everything that's not in the A circle. And I suppose this box around the outside is where I've stopped colouring. That's the set S. That all of these are subsets of S. And on the right, I have I'm going to say A minus B, A but not B. The set difference there, things that are in A but not in B. And in my picture, you'll notice that I've got B as still some large circle, maybe including some other stuff, which is it's not relevant, it's not coloured in, but again, I don't want you to assume that B is a subset of A. Okay, this word comes up quite a lot. I'm going to use it quite a lot. We say that two sets are disjoint if their intersection is the empty set, if they have nothing in common. So on those diagrams, I might have nothing, no overlap, so no actual examples of things that lie in the middle. We say disjoint, and it works both ways, of course. So I might say that A is disjoint to B if I'm particularly highlighting that direction, but in that case, B is also disjoint to A. So more commonly, people just say that A and B are disjoint. There's also a phrase mutually disjoint, where you have maybe some larger collection of sets, A and B and C, and you want to say that any pair of them is the empty set. Although be careful with that, because that's different from requiring that the intersection of all three is empty. So not quite the same thing. Okay. More generally, I've mentioned it there by talking about a third set C. We can do unions and intersections of arbitrary many sets. The notation for this is a bit like the notation for a sum. Instead of using a big capital sigma, we use a big union symbol or a big intersection symbol. I think these symbols are called cup and cap, if you're interested, but it's a bit like a U and an upside down U, but not quite. Anyway, here I'm being quite general about how many of these I've got. So underneath I've written I in some set, capital I, which is called an indexing set. If you like, it's the subscripts here. It's all of the possible subscripts that I might want. So once I've set that up, I've got lots of subsets. Instead of calling them A, B, and C, I'd quite like to call them A1, A2, and A3, so that I can do things like this without having to write, intersection over the alphabet or something. Like A1, A2, A3 is really nice because then I can tell you what I want. Intersection over all of these things means it's really strict. You've got to be in all of them. X in AI for all I in the indexing set, which I'm writing it up. Generally, it might be the set curly bracket 1, 2, 3. If I just want to talk about three things, in which case I probably wouldn't set it up with all of this. I would probably just say you have the family of subsets A1, A2, A3, close curly bracket. But here we are. So intersection means you're in all of them, and union is very permissive. It says that you have to be in at least one of them. I don't mind which. And on screen, I'm being vague about how many I've got. This indexing set could be quite large if you like, but that principle still holds. Intersection, you've got to be in all of them, absolutely all of them. Union, you've just got to be in at least one of them. More than one is fine. Just one, that's fine. Union's permissive. It might be a subset of the naturals, and in particular, if it's a nice subset of the naturals, like, for example, all of them, or the first n of them, then people write things like this, which is a bit like sums. So you've seen sum from I as 1 to n. Same rules apply. So you start with the value down here, you stop with the value up here, you include both of those values. So this would be the intersection of A1, A2, A3, A4, all the way up to AN. You've got to be in all n of them. And on the right, people write infinity on the top if they want to include all of the naturals. If they have a set AI for every integer I, in which case they might write something like this. For the union here, you are in one of these subsets for some natural number. And in some of these cases, the fact that it's natural numbers is understood from the context, or sometimes it's understood from the way that they've set up their subsets AI. They should probably define what the AIs are before they start telling you to take unions of them, but here we are. It could be a larger set, in which case it should be quite clear. If that seems strange, you can have quite a lot of sets. We've seen this. We've seen the set of reals is quite large, which means that its subsets, there are many. There's a subset for every real, isn't there? The subset that just contains that real. So you can have quite a lot. Oh gosh, that's a terrible curly brace. So you can have quite a lot of sets of reals, and these are just the ones with one element, the confusing ones from before. There are other subsets of the reals, but just these ones, I could index them by saying AI is the set just containing I for each I in the reals. That would be a lot of subsets of the reals, each with just one element. I'm not even thinking about the subsets that have more than one element. Those ones would have union equal to the reals, stitch them all back together again to get all the reals, and intersection the empty set, because they're all disjoint. Any pair of them is disjoint, because they just contain one element each. Okay, but that's an example where you can index with not just the numbers. People don't do this for sums for a good reason. Adding together infinitely many things is already quite dangerous. You'll learn about that in the analysis course. Okay, right, intersection unions, bit better behaved though. Okay, that's intersections and unions. Where am I going with this? I want to show you an example with some students at Oxford, since that's where we are. Big universe of objects today is the set of all students at Oxford, including you. So let's say A is the subset of students studying mathematics. B is the subset of students at your college. Then those are two different subsets. A intersect B is the set of students who are both studying mathematics and at your college. That's maybe the 6 or 8 of you who turn up to lectures together. A union B is the set of students who are either at your college or studying mathematics, and probably that set contains a lot of your friends who you've met either in college or in lectures. B complement is the set of, let's think, so B was the ones at your college, so B complement is the students not at your college, and the set difference A minus B is the set of students studying mathematics at other colleges who you meet at lectures, not to be confused with the set B, set difference A, which is the set of students at your college not studying mathematics, who might be living next door to you. Right, okay. Applications to life at Oxford, there you go. Here's the maths examples. So irrational numbers, that's the set of things that are real but not rational. This contains things like the square root of 2, but I'm not going to prove it right now. Maybe you've already seen a proof that the square root of 2 is real but not rational. Actually, probably you've only seen a proof that it's not rational. I wonder if you've seen a proof that it's... No, never mind. It's real but not rational. And some people define the set of natural numbers, which we had right at the start, to be what I would call natural but not zero. And here's another example of a set containing one element. That's the set containing 0. I have to do it like that because the notation of set difference is only defined when that's a set. So this, no, don't do that. If you're doing set difference, you need to have a set. I realise it looks like it says no as well, so maybe that's how you can remember it. You've got to put curly braces on that, so that I know to look at elements of the naturals and to look at elements of your set that you're doing set difference with, so that I know, oh, it's 0 that's not included. Reminder, for me, 0 is a natural number. I suppose if 0 is not a natural number, then the thing up there is still defined, it's just equal to the naturals, because set difference wouldn't be removing anything if 0 is not in naturals for you. Anyway, right, this is a reminder that set with one element, you've got to write the curly braces to show me that it's a set. Okay, double inclusion. This is really important. If you like, this is the definition of sets being equal again. We saw this in the previous video to look at what it means for sets to be equal. We said that every element of the first set has to be in the second set and vice versa. Every element of the second set has to be in the first set. The principle up here of double inclusion is that you can write that with subsets. The idea is that sets are equal if and only if A is a subset of B and also B is a subset of A. So we've got a proof of this. It's if and only if up here. So I need to go in both directions. I'm going to start with the forwards direction. So if A and B are equal, then every element of A is an element of B. So certainly A is a subset of B. So this is using our definition before about the elements and saying you can write that as A is a subset of B. It matches the definition. And the other half of our definition, that every element of B is an element of A, means that you have B as a subset of A. It's an if and only if statement up there, so I need to go the other direction as well, which says, suppose that you have this double inclusion property. These are inclusions. If you think of subset as being these elements are included in B, so it's double inclusion because there are two of these inclusion statements. So if A is a subset of B and also B is a subset of A, then the conclusion is that they're equal. Here we go. For every element of the set S, so it's a wider collection, if X is in A, then because A is a subset of B, it must be the case that X is an element of B. That's what subset means. And if X is not in A, then because B is a subset of A, using that one, that means that X can't be in B. So that's a little bit like using the definition in the other direction. Remember, subset means if you're in B, then you're in A. I'd like to consider what happens if X is not in A. Well, it can't have been in B. If you like, that's a very small proof by contradiction. Say, suppose what would happen? Could X be in B? Well, no, because then it would be in A, and we've just said it's not, so it must be the case that X is not in B. That mini proof by contradiction has a name. It's called contrapositive. We will see more about it in a later chapter. Anyway, so you can go in both directions. Where did I get to? X is in A if and only if X is in B, because we've checked both cases in A and not in A, and reached our conclusions in B, not in B, respectively, which means that X is in A if and only if X is in B. So those sets are equal. That's double inclusion, but as I say, you can use that as your definition for what it means for sets to be equal. It's important because it gives you a way to prove that sets are equal just by looking at subsets. And often those two properties do separate out, so you might check these two things separately. We've got some examples coming up in the next couple of slides, but this might come up in other places as well. And it might be more disguised that you might have both of these facts, which look quite different and maybe read quite differently because they're the other way around from each other. The conclusion that you can draw is that those sets are equal, and it might not always be obvious from the way that you've written out the subset statements. Okay, that's a bit vague. Let's look at some examples. So suppose we've got three subsets, then I have these things called distributive laws, which tell me how union distributes across the intersection. If you like, obviously this is not a proof, don't copy this down, but the reason it's called distributive is because it's like something like if you've seen 3 times 2 plus 5, you know that that's 3 times 2 plus 3 times 5. And if you really squint, then the union symbols here and here and here are in the same places as these multiplications. And the addition sign in here is in the same place as the intersection signs in the statement. So this distribution of multiplication across addition is maybe the first time you meet distributivity, but it also applies to other operations like this. So here we're looking at distributive laws for intersection and union, talking about subsets of set S. I just want to make the point that you've seen something like this before, and now we're doing it in a different context, but similar shape. Okay, the proof uses double inclusion, so that's how we're going to do this. On the left, I've got A union, and then in brackets, B intersects C. Suppose that you're an element of that. Then that means, reading the outside bit, that you're in A, or you're in this thing on the right, B intersects C. You have to be one or the other. Maybe both, but I don't care if you're in both. That's nice. Either X is in A, that's the first case, or in this case, X is in both B and C, which is amazing. Great. If X is in A, then it's definitely in A union B, this thing here, and it's definitely in A union C from the definition of those things, and because it's in both, it's in the intersection of those things. So that's one possibility, that X might be just in the left-hand side because it's in A, in which case it's definitely in the right-hand side because it's in here and it's in here. That means it's qualified to be in the intersection. Therefore, X is in the intersection. I also need to check this idea that if X is in both B and C, it's on the next slide, but while I'm here, it's going to be that, well, it's in both of these bracketed terms for exactly the opposite reason, right? That it's in B, so it's in this, and it's in C, so it's in this. It once again qualifies to be in the intersection. So let's go to there. Here it is. So final bit, if X is in B and C, then it's in both of these things for a different reason, but it's in both of these things. So every element of the left-hand side is in the right-hand side. That's half of the proof by principle of double inclusion. We now need to do a sort of other direction. We've shown that every element of the left-hand side is in the right-hand side. So conversely, we're going to try and show that every element in the right-hand side is in the left-hand side. So for this bit, we suppose that x is in the thing on the right hand side. A union B intersect A union C. So what does that mean? That means that x is in both of these bracketed things, A union B and also A union C. So here we go. Either, looking at this one, either x is in A, or if it's not in A, then it's in B. And also, actually looking at this one, if x is not in A, then x is in C as well, because of how the union works. That if you have to be in at least one, so if you're not in A, then you must be in B, and over here, if you're not in A, then you must be in C. So x is in, new line, sorry, x is in A union B intersects C, because it's either in A, or the other case is better, it's in B and C. So that means that we've got to the left-hand side now. This means that the right-hand side is in the left-hand side. That's written out here. Right-hand side is in the left-hand side. So by double inclusion, we've gone in both directions now. The left-hand side is in the right-hand side. The right-hand side is in the left-hand side. My camera is mirrored. I'm sorry for that. Left hand. My left hand is on the right. I can do this. The left-hand side is in the right-hand side, and the right-hand side is in the left-hand side, so they're both equal. Good. We're not going to do a proof of 2, which has a very similar structure, to chase elements from the left-hand side over here to the right-hand side, and vice versa. But if you do that, then you can check that those statements are also true. This one is not true with addition and multiplication. If you follow through the example I was drawing on the right, it's not true that addition distributes over multiplication in the same way that multiplication distributes over addition. But something rather nice is true for subsets of a set S. The intersection and union play nicely. I think I've got one more example of a proof with De Morgan's laws, which we're going to look at quite quickly. Again, this is double inclusion. These are statements about how complement works with unions and intersections. So it's combining together ideas from the definitions at the start of this video. So for A union B, the complement of that, De Morgan says, is the complement of A and the complement of B. In words, I would say, if you're not in the union of A and B, then you're in neither. You're not in A and you're not in B. And separately, there's this other law. If you're not in the intersection, well, that means you're not in both. So what's the problem? You're either not in A or you're not in B. Yeah, maybe you're in neither, maybe both, but union is permissive. Union allows both. Okay, so we're going to prove the first one with double inclusion on the screen here. It works like this. Suppose that x is in the left-hand side, the complement of A and B. So x is not in either A or B. So x is in the complement of A and it's in the complement of B, because it's not in A and it's not in B. Because it's in both of these sets, it's in the intersection of these sets. And that shows that everything in the left-hand side is in the right-hand side, and then going in the other direction, everything is in the right-hand side. So x in A complement intersect B complement would mean that x is not in A and also x is not in B. So x is in neither, which means that it's in the complement of the union. So everything in the right-hand side is in the left-hand side. So with double inclusion, those things are equal. Following these things through with this mix of sets and logic is not my favourite. We're going to see a more streamlined proof in a future chapter when we get down to some logical notation. But we're also going to see a proof using truth tables in the next video. So if you'd like to see something a bit more systematic that gives you a way to prove things like De Morgan's laws or the distributive properties we were just looking at, then you might like truth tables, which are coming up in the next video. See you there.